Good afternoon, everyone. Hope everyone's doing okay. Let's see. Let's just wait another minute. Let people get here. Just in case I don't think I posted the video from Monday's meeting, but if you weren't there, then you probably are unaware that I had to cancel class. Like, I don't even know how far we were into class, maybe 10, 15 minutes, and I had to go with an emergency. So there's no real video. I'm going to kind of run through everything again quickly so that everyone's on the same page, and then we'll pick up where we left off and start doing these quadratic functions. So are there any questions before I start?
Is the quadratic function pushed back, or is it still due today? Homework?
Oh, you know what? I forgot to do that. Yeah, don't worry about that. I apologize. I will adjust the due dates. We've lost another day. So all right, so let's get into this. Last time, like I said, we started talking about quadratic functions, and the main idea was that when it comes to quadratic functions, number one, they don't look like lines at all, right? They look like these things called parabolas. And we have two forms that we can see them. We can see them either in standard form, where it looks like ax squared plus bx plus c, or the vertex form, which looks like a times x minus h squared plus k. I told you that both of these forms have pros and cons to them, and that we have ways of converting from one form, back and forth. If you want to go from standard to vertex, we have a way of doing it. If we want to go from vertex to standard, we have a way of doing that. I did not show you how to do that yet, but I told you that there's a way to do it. So after that, we started talking about just like the general look of a quadratic function, that they give you either, they give you parabolas that either open up or down, and that what determines whether or not it opens up or down is simply the number that's in front of x squared. That number right there, a, is what determines if you have a parabola going up or down. And we said that if a is positive, it's going to open up, and if a is negative, it's going to open down. We also talked about the vertex, which is this very important point on every parabola. If it's a parabola that opens up, the vertex would be the lowest point on the graph. And if it's a parabola that opens down, then the vertex would be the highest point on the graph. And it always corresponds to some point, right? It's a point. So we give it an x and y coordinate. And the x and y coordinate, we don't call it x and y, we call it h and k. And then we started talking about x-intercepts. We said when it comes to parabolas, there's really only three different scenarios we can have with x-intercepts. We can have none, we can have one, or we can have two. So I have a little illustration here for us to kind of go through that again. Here's an example of a parabola that opens up and has no x-intercepts, right? Does not hit the x-axis. I can move it left and right. That still would not change the fact that it does not hit the x-axis. So that's an example of having no x-intercepts. An example of a parabola that would have one x-intercept would be something like that. We could even flip it over. That would still only have one x-intercept right here. And then the other case is where you actually have two x-intercepts, like here and here. So again, three different scenarios when it comes to x-intercepts. We either have none, one, or two. And that's kind of where we were when I just had to stop. So the next thing we want to talk about are y-intercepts. So for all quadratics, you have, okay, y-intercepts. Let's look at the graph. So look at this parabola here. How many times does it hit the y-axis? Once, right? Just one time, right? If I change the shape, if I make it look like that, it still hits once. If I make it move open up, I still have one. What if I make it really, really narrow? What if I make it really narrow like this? Does that still hit the y-axis?
Yes.
Yes. Once, right? Way up here. We'd have to zoom out and go find it, but up somewhere there it hit the y-axis, right? So it turns out that all parabolas, as long as they open up or down, because there are parabolas that open sideways, we are not going to study those here yet. We will study them later, but we are not going to study the parabolas that open up sideways. The reason we're not is because, let me go ahead and show you one. There's one that opens up sideways. The reason we're not studying these right now is because this is not a function. It fails the vertical line test. So we are only talking about functions right now, and that means our parabolas have to open up or down. Okay, so we're not looking at that at all. So for us, all quadratic functions of the form that we're talking about have one, right? One y-intercept. Now, there's a couple of other things we want to talk about, all right? This one is more of a visual thing. If you look at a parabola, every parabola that you ever draw will have some imaginary line. Here, let me graph it for you. Right there. So you see that imaginary line right there? That imaginary line, hold on, I gotta change one thing here. H, there we go. That imaginary line is not part of your graph, but it cuts the parabola right down the middle. And the parabola is symmetric to this line, meaning that if you were to take the left side of the graph and reflect it over that line, right? Reflect it, it would land right on top of the other side. And that will happen for all parabolas. They have this imaginary line right down the middle that creates this reflection. They call it a line of symmetry. And it doesn't matter how I shape the graph, right? If I change the shape of the graph, I will still have that line there. If I move it to the left or to the right, I will always have that line. Even if I move it up or down, I still have that line. So that line has a name. It's called the axis of symmetry. So we need to be able to identify that. So all parabolas, all quadratic functions, I'm going to abbreviate here, have what's called an axis of symmetry. Like if that's my wife, I'm gonna freak out. Okay. Okay, axis of symmetry. Okay. So that's pretty much it. All right. When it comes to parabolas, I think we've identified all the important aspects of a parabola, right? We have opens up or down. We have this vertex point. We could have 0, 1, 2, or 3 x-intercepts. I'm sorry, 0, 1, or 2 x-intercepts. We must have a y-intercept, and they all have this vertical imaginary line that creates this axis of symmetry. Okay, that's what we've got for all parabolas. So our goal here today is going to be to see if I give you a quadratic function, can you graph it? Okay, can you actually draw it for me? So we're going to do that, but before I do it, I wanted to talk about parabolas just more generally, because I think it's important for us to understand the importance of parabolas in the real world, and maybe that'll make us a little more interested in studying them here. So parabolas, there's many different places in the real world where they show up. The most simple example I can probably give you is to just think about taking like a ball and throwing the ball through the air, right? Take a baseball. So if you were to take a ball and throw the ball through the air, you know, it'll go and land and hit the ground, right? Over here somewhere, it'll hit the ground. And that path of the ball through the air is a parabola. Okay, always, okay? As long as you're on a planet that has gravity, if you throw something through the air, it's gonna travel in a parabolic path, which means there is some quadratic function, okay? there's some quadratic, we don't know exactly what it is right off the bat, but there is some quadratic function which actually represents this physical motion of the ball through the air. Now, that actually would become important at some point. You might want to know the exact path of a ball through the air, because I don't know, maybe you want to know if you throw a ball through the air, you want to know where it's going to hit the ground, you know, and where it hits the ground would correspond to an X-intercept, right? Or the highest point on the graph would be how high that ball goes. That would correspond to the vertex. Make sense? So it's useful. Now, in the real world, if you look back through history, it's actually kind of sad how this all became important to us. If you think about it, it really goes back to like warfare and our I guess the fact that we don't get along pretty much as humans. I mean, we like to fight over things. So, you know, when you're think about like a castle, you know, you got this castle and, you know, these people that live in this castle, that's a really good castle, I know. So you know, all these people live in this castle and they've got, you know, food and they've got, you know, different things that, you know, precious metals, whatever. They've got whatever the wealth of those people were is all in that castle. Then you got these other people that want to come and take it from them, right? Because they basically don't believe the same thing. So they want to storm the castle. They want to start lobbing things into the castle, right? And they don't want it to go too far. They don't want it too short. They want to get in the castle, right? Terrify these people, make them give up. Well, every one of these things that they lob through is parabolic, right? So if you can have some understanding of the mathematics behind that, you can actually be very accurate with where you put your projectiles. So, you know, historically, this kind of need to improve our abilities in warfare pushed math and science, right? And it still to this day does, right? A lot of the technological advances that we have are a result of either preparing for war or during war we learned something, right? I don't know if y'all know this, the internet, y'all know that why the internet was created? Anyone know why the internet was created? No? No?
Communication. Just military communication.
Military communication. So the idea was, and I'm going to draw the United States right here. So again, don't be jealous of my drawings. I know it's many, many years of doing this for a living. I've gotten really good at it. So you know, there's the United States. So the idea was we were always at war with the Soviet Union over on the other side of the world, and there was this big arms race and everything. And what we were afraid of, everyone had, you know, they had nuclear weapons, we had nuclear weapons. This was the former USSR, USA, right? And so we had all these nuclear weapons pointed at them. They had all these nuclear weapons pointed at us, and it was just waiting for someone to pull the trigger. Well, we had major command centers in different parts of the United States, and we were afraid that if they took out one of them, that it would break our communication chain between the military branches. So we said, how could we make it so they couldn't wipe out our communication ability? So what we did is we said, well, let's use the phone lines, because the phone lines are everywhere. So even if you knock out some of it, you'll still have some where everyone is connected with these phone lines. And so it's not centralized. And so you'll still have the ability to communicate even if they wipe out an entire city of phone lines. So that's basically the way it was started, was the idea that you wanted to decentralize communication in the military. And the bad thing is, you know, once you start that, you can't undo it, right? So like, you can't just like turn it off now, right? But again, technology, war, everything like that has pushed our math and our science to the next level. Nuclear weapons were created out of the need to stop a war, right? Or to be the first one to get a nuclear weapon. So understanding a parabola, as simple as that may sound, right? Understanding a parabola is actually was important, right? Now there are other places that they come into play. When you talk on your cell phone, right? I mean, this is something we take for granted, but if you're sitting there in your house, right, and you make a phone call, right, Your phone is sending out electromagnetic waves out in every direction. And somewhere near your house, there's got to be a cell phone tower, okay? And that tower is just constantly listening, and it's going to intercept, it's going to get that signal that's coming out of your phone, and it's going to hear it. And the way it hears it is through a parabolic shaped receiver. And so parabolas have a very unique property. All parabolas, when you draw them, if you were to shine a light in, and let's say it was a mirror, it would bounce off that mirror and it would go somewhere, right? And every single light beam that came in, they all happen to bounce to the same place, no matter what. Now, only a parabola will do this. If you just take half of a circle, it doesn't do this. Only parabolas. So everything, all these things get focused onto one point, and we call that point the focus. So when these towers are sitting there, they've got these parabolic receivers. They're listening, you know, think of it like ears, and they're getting that signal and they're focusing it onto this receiver, and that's how it hears you. And then once it hears your signal, it sends your signal out, and there's other towers listening, and that tower catches your signal. And it's the same thing repeated over and over, and it goes from tower to tower to tower until it gets to the person that is receiving your phone call. So parabolas are necessary for communications, right, through phones. Now, if you want to call someone around the other side of the world, assuming that the world is round, right, then you can't have towers because you got oceans between the continents. So what we do instead is you still send your signal out, some tower catches it, but then it says, oh, I know that this call is going to around the world. So it sends that up to a satellite dish, right, sitting in space. And that satellite dish sends it over to another satellite dish, and then back down to a tower, and then to the person. So those satellite dishes, when you draw a satellite dish, it looks like this. I think everyone would agree this is kind of what a satellite dish looks like. That's a parabola. It's a parabolic mirror, so to speak. And that little thing right there is the focus. That's where all the everything that goes in there bounces off and goes to that focus. So again, parabolas are simple. Mathematically, it's pretty basic function, but it's used everywhere, you know, in our communications and in other places too. Your headlights on your car, right? Use a parabolic mirror behind the headlights so that you get a beam of light to come out. Okay, it's parabolas. Okay, so that's it. That's all I want to say about that. All right, so let's get to how are we going to graph this, right? So set of steps. How to sketch quadratic functions. The first step we're going to do is we're going to determine if it opens up or down. Now, this step should be easy because the only thing that tells us whether or not it opens up or down is that A that's in front of the x squared. So that should be easy, right? We just look at the number in front of x squared. If it's positive, it opens up. If it's negative, it opens down. So that should be fine. Step 2 is going to be for us to find the vertex. Now, when it comes to finding the vertex, you have to remember that when you're doing a parabola or quadratic, remember I told you there was 2 forms of a parabola. Maybe I should put those up here. The first form we called standard form was this. The other form was this one. Right? So this was standard form, and this is what we call the vertex form. So when you're trying to find the vertex, it's very easy. This is very easy if you are in this form, because the vertex will be the H and then the K. And that means you'll be able to just look at it and tell me what H and K are. Now, if you have this form, the vertex is a little harder. Okay, so if you have this, then I have to give you a formula to find the vertex. Here it is. The H will be equal to negative B over 2A, and the K will be the function evaluated at H. So this is called the vertex formula. And that formula actually comes from calculus. When you're in calculus, hopefully your calculus professor will show you why this is true. For us, we're just going to use the formula, just take it on faith and be happy. So again, if we're trying to find, well, determining if it opens up or down should be easy. We just look at the A. The vertex might be easy if we have it in this form, but if it's not, we're going to have to crank out a little formula. All right, so now we have, think about this. We know so far the graph, we'll know if it opens up or down, and we'll know the vertex, which is either the highest or lowest point, depending on if it opens up or down. The third step is something that the book, and pretty much anyone I've ever talked to that teaches this class, they don't do this third step. I do it. I don't know why. I just like it. What I do next is a quick sketch. I do a very quick sketch using the information I have right up to this point. Now, here's why I do a quick sketch. We don't know how many X-intercepts we have, right? Like in general, if someone just gives us a quadratic function in either one of these forms, there's no easy way to tell just by looking whether or not it has 0 X-intercepts, 1 X-intercept, or 2. We don't know. But with a quick sketch, we should be able to figure that out. Think about it. You know if it opens up or down, right? You know that, and you know the vertex. So, you know, let's just say that I do a quick sketch and I know that it opens, let's say it opens up. Okay, so let's say this one opens up, and let's say I determine that the vertex is the point 4, 3 is my vertex. So basically I've done steps 1 and 2, and I know that it opens up and it has a vertex of 4, 3. That means I go to the right 4 and up 3 and I draw a dot. If my parabola opens up, it has to go like that, right? Which means I have how many X-intercepts?
None.
None. So I won't go try and find them. All right. I will skip this step of trying to find X-intercepts because I don't have them. I'm trying to keep us from wasting our time. Here's another scenario. What if it opens down and my vertex was the point 4, 3? Well, same thing. I go to the right 4, I go up 3, I just draw a point, but now I know it opens down, right? So in this case, I would go look for the X-intercepts because I know I have 2 of them, right? So I want to go try and find them. Another scenario we could have, what if we have a vertex, what if it opens up and we get a vertex of 5, 0? Well, that means we go to the right. Yeah. And then we just draw a point and it opens up, right? We only have 1 X-intercept, don't we? But it actually is the vertex. The vertex is actually also our X-intercept. So really, this is a way of just trying to cut down on time. All right. We do our quick sketch to determine the number of X-intercepts we have. Now, step 4 is to find the X-intercepts, if you have them. Right? We will skip step 4. In both the cases here, I'm highlighting in, no, not that one, sorry. In this case here, Or in this case, I would not do step 4, right? I would not do step 4 because it's a waste of my time. Now, the question is, how do you find X-intercepts though? We haven't discussed that. So this is actually a broader concept. In algebra, if you're given a function, how is it that you determine the X-intercepts for any function? What do you do? Who knows?
Set y equal to 0.
Set y equal to 0. Well, in this case, y is f of x, right? Y is the function. So I'm going to write it this way. It's the same thing, but I'm going to say set the function equal to 0 and solve. Now, for us, because we're talking about quadratic functions, that means we have to set these equal to 0, right? Which means you have to be able to solve a quadratic equation. And so I personally think that most of the time, this is the hardest part of the whole thing. Because solving a quadratic equation is not always straightforward. Sometimes there's some work involved. So we will get to, as we do examples, we'll get to how we do that. The 5th step is to get the Y-intercept. Are we always going to have one?
Yes.
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 Okay, so how do we find them? How do you find the Y-intercept? To find the X-intercept, you set the function to 0. How do you find the Y-intercept?
Setting x equal to 0.
Set x equal to 0. In other words, all you have to do is plug 0 into the function. And that answer, the answer you get out when you plug 0 in for x, is the Y-intercept. The 6th step is to do the sketch. So you basically put all this information together and you draw a final picture. So these are the 6 steps that I'm going to follow, and I think it's time for us to do some examples. Okay, first example.
What was the last step?
Sketch. The last step is to sketch. So sketch the function f of x equals, let's start easy, okay? So. All right, what I like to do first is identify a, b, and c. So I like to identify the number in front of x, the number in front of, I'm sorry, x squared, the number in front of x, and the number by itself. So a for us here is 1, b for us is -4, and c is -12. Would you all agree with that? What form do we have here? Is this standard form or is this vertex form?
Standard.
Standard, right? So this is standard form. All right, that sucks. Okay, standard form. All right, so here we go. First step. Does it open up or down?
Up.
Up. It opens up. It opens up because a is 1, and that's a positive number. So it opens up. So I know that much. Step 2 is to find the vertex. Now, because it's in standard form, I'm going to have to work for the vertex. I've got to find h first. And the formula that I gave you for that is that you take -b and you divide it by 2 times a. And I said that that formula comes from calculus, so we're just going to use it. So when I write here -b, it's the opposite of b, right? So for us, b is -4. So we're going to do -4 over 2 times a. So 2 times a was 1. So we wind up getting 4 on top and 2 on the bottom, which is 2. That's how we find h. It's just plug and chug, right? Just plug in numbers, crank out the answer. K, on the other hand, is what you get when you plug that answer 2 into the function. So it's really kind of important to understand that if you mess up h, right? If you mess this up, k is going to be wrong, right? So you got to really make sure you get your h right. So now I plug 2 into the original function, which means I just replace all the x's with 2's. And for this, I get 4, take away 8, take away 12, negative 16. So my vertex is a point. It's the point 2, negative 16. Questions? Step 3, quick sketch. And like I said, this sketch is not our final answer. This is just to determine how many x-intercepts we have. So when I say quick, here's what I mean by quick. Okay, where's my vertex? To the right 2, down 16. So I'm just going to go right and down. I don't even care how far. My vertex is somewhere down here, right? Right 2, down 16. And my parabola opens up. I know that because part 1. I'm not sure where, but I can see from this that I have 2 x-intercepts, right? So that means I'm going to have to do step 4. If this parabola had opened down, then I would skip step 4. Understand? Step 4, the x-intercepts. So to do that, I need to set the function equal to 0. X squared minus 4x minus 12 equals 0. And now we've gotten to a point where, well, this is going to depend on you, all right? How comfortable are you solving quadratic equations? We have 2 ways to do it. First way, we could try and factor. Does this factor? I think it does.
Yes.
It does factor, right? So if you're comfortable with factoring, which I hope you are becoming more comfortable with factoring. Unfortunately, in this class, we don't spend a bunch of time learning how to factor. We kind of assume you know how to do it. So if you are having trouble with this, it's definitely something you should review because it'll catch up to you, especially in pre-cal and cal 1. All right, so this does factor to be x minus 6x plus 2. And once you have it factored, you can set each factor equal to 0. And you should get 2 answers, positive 6 and negative 2. Those are x-intercepts. So that's how you do it with factoring. What's the other way? Does anyone know the other way I could have solved this?
The quadratic equation.
The quadratic equation, or the quadratic formula. So we have a formula that's actually very nice. It's a formula called the quadratic formula. I'm sure you've all seen this before. It says that if you have an equation, ax squared plus bx plus c equals 0, that you can get the answers without really doing anything but plugging certain things in to this formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. That is your quadratic formula. So all you need to know is a, b, and c. Plug in, you should get your answers. So I'm going to do it on this one just to kind of illustrate that it can be done. We'll get the same 2 answers. I've got to have my a, b, and c here, though. I'm just going to pop them right here so I can see them. This was our a, b, and c. So what we know is that the solutions to this are x equals, first thing in the formula is negative b. So that's negative negative 4. That gives me positive 4, plus or minus the square root. Then I have to square b. So what is b squared for us? What happens when you square b?
It becomes just positive 16.
Positive 16. Good. Minus 4 times a, which is 1, times c, which is negative 12. The entire thing divided by 2 times A was 1. So in math, we call this plug and chug. That's all you're doing is plugging in numbers, chugging out the answer. You just have to be careful not to make mistakes with the signs. 4 plus or minus square root. Okay, I always tell my students to do all of this first, do all that. And I also tell them just ignore the minus sign right now. Just ignore that, okay? We'll come back to that. What's 4 times 1 times negative 12? So 4 times 1 times negative 12 should give you what?
Negative 48.
Negative 48, right? Now, we had a minus sign in front. I kind of hit it here, but we had this minus sign. So it's going to be 16 minus negative 48. And then all over 2 times 1, which is 2. 16 minus minus is plus. So 16 plus 48 gives us 16 plus 48. 64?
I think so, yeah.
Now, the square root of 64 is actually a number that we know, hopefully, right? 8. So this becomes 4 plus or minus 8 over 2. And then at this point, this is where I like to take this and realize that this is 2 different answers. The first answer is what happens when I use the plus from the formula. And the second one is what happens if I use the minus in the formula. So if I use the plus, it becomes 4 plus 8 divided by 2, which is 12 divided by 2, which is 6. And if I use the minus, I get 4 minus 8 over 2, which is negative 4 over 2, which is negative 2. And those answers match exactly with the answers we got by factoring. So I think factoring was much more efficient, but in case the factoring falls through, you have a backup of the quadratic formula. And there are going to be problems we do today where you cannot factor, so you have no choice but to use this. All right. Any questions? All right, step 5, the Y-intercept. So for this, all we do is plug 0 into the function. And that should be pretty easy to plug 0 into this. We're just going to have 0 squared minus 4 times 0 minus 12. You should get negative 12. I'll also point out, if you, I don't know if you caught this or not, but if you're given a quadratic function in standard form, the Y-intercept is always C. Because if you plug 0 in for X here and here, these go away and the C will always be your Y-intercept. Now it doesn't, this in the vertex form, it doesn't work the same way. Because if you plug in 0 here, it doesn't kill all this off. So the K is not the Y-intercept. But for standard form, the C will be the Y-intercept. All right, we've got everything. We're ready to draw the picture. So here we go. Gonna start with my XY axes here. This may not be big enough. Let me see, maybe a little bit bigger. Try that. All right, so let me start with the vertex. Where was the vertex again?
2, negative
Negative
16.
6.
To negative 6?
16,
16. Oh, crap. Okay. So I'm going to go to the right 2 and down 16. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Shit, it's way down there. Negative 16. So my vertex is right here. Now my parabola opens up, I know that, right? So I'd like to know where it hits the x-axis. And we already found that that was what, negative 2
and 6.
and 6. I also have a y-intercept of negative 12. So it should hit the y-axis here at negative 12. So should be right there at negative 12. Yeah. Now,
Yes.
this is not part of the graph, but I'm going to draw this imaginary line down the middle. That is my axis of symmetry. What I need to draw now is a parabola. So it needs to look like a U, not a V. Must be a U shape. And it must be symmetric. So I actually have 2 points on the left side. So I'm going to start with the left side, try and make this look a little curved. It's hard. Not bad. And then on the other side, I try and basically just draw like the same thing mirrored over. Now, look, you don't have to be perfect with this, okay? We're not trying to land a man on the moon here. But what I will say is that it's important that you label things so that it's easy for me to see where your vertex is. So I can see that the vertex is at 2, -16. If you want, you can label it. That would be even better. You could label all your points 6, 0, label this point -2, 0, and even label the Y-intercept 0, -12. And then I have basically everything I need. That right there is what I'm looking for. All right. We could then talk about domain. We could talk about range, right? We could talk about where the graph is increasing, where it's decreasing. All the things we were doing before, we can start talking about. All right, I think that was a very basic one. Let's do a different one. Let's do one in standard form. Let's see how much different it is. I mean, not standard form, in vertex form. So for this example, same thing. Let's sketch f of x equals -2 x plus 5 squared plus let's go 8. All right, so you have to understand that that's a parabola first, right? First step, it opens which way? Down, right? Opens down. And that's because A is -2, which is less than 0. So we know this thing opens down. How about the vertex?
It's 5, 8, right?
Yeah, so it has, because it's in this form. Let me write the formula down for the vertex formula, or the vertex form of a quadratic. So here's the vertex form, which is what we have here, right? A is -2, and then the K is 8. That's easy to see. Be careful with the H, because in the formula it's -H. Here you see we have +5.
Which means it's -5.
That's right. The H will always be the opposite of what you see. So if we see a +5 here, H is actually -5. So I don't have to do much work for the vertex. It's going to be -5, 8. Any questions on that? The opposite of what you see here is H. Whatever you see out here is K. So 8, +8 is K. Third step, quick sketch. Quick. Okay, -5 to left 5, up 8. I have a vertex here. Which way do we open?
Down.
Down.
Which means we'll have 2 X-intercepts.
2 X-intercepts. 2 X-intercepts. So that means I have to go find them. So far, it's been pretty smooth though, right? A was pretty easy. The vertex was pretty easy. The X-intercepts, I do have them. I need to take the original function and set it equal to 0. Now, please pay attention. When we have the vertex form, it is easiest to not do the quadratic formula, okay? Because the quadratic formula works best when you have the standard form. If we have the vertex form, we can't use this formula because we don't have B and C. We only have A. So the way you go about this is actually easier than the quadratic formula, I think. You're going to try and isolate this by itself. So I'm going to move the 8 to the other side, which will make it -8. I will then divide both sides by -2. You get x plus 5 squared equals -8 divided by -2 is 4. Any guess as to what I'm going to do next?
Factor.
Square root of both sides.
I'm going to square root both sides. Square root. And remember, when you come in and square root both sides, you have to do plus or minus. You have to look at both cases. So when you square root the left side, all you get is the x plus 5. And on the right side, well, the square root of 4 is 2, so you get two answers, positive and -2. And we almost have x by itself. We just need to subtract 5 on both sides. So plus or minus 2, take away 5. And that gives me two different answers, the plus case and the minus. So if I do the plus, it's 2 minus 5, which is -3. And if I do the negative case, it's -2 minus 5, which gives me -7. Does that all make sense? What I'm doing there? Yeah. Okay. I am cranking along here. What's next? I forgot.
Find the Y-intercept.
Y-intercept. Okay, so here we have to plug 0 into the function, right? All right, that's not gonna be as easy as it was before. I'm gonna have to plug 0 in for the x, like that. So I go to the original function, I replace the x with 0. This gives me -2. Now 0 plus 5 is 5, so I have to take the 5 and square it and add 8. So order of operations, just be careful here. -2 times 25, square the 5. Then multiply times -2, -50 plus 8. Man, that's going to be a crappy Y-intercept. It's way down there at -42. Shoot. All right. Such is life. That's the reality of the world we're in right now, okay? That's what we have to handle. So we're ready. Let's go graph it. All right, so my vertex was at, where was it?
5, 8.
-5, 8. -5, 8. What, it was -5, 8, yeah, up. Okay.
Yeah.
So I'm starting to think about how I want to do my graph. My vertex was -5, 8. My x-intercepts were where?
-3 and -7.
-3, -7, but I had a y-intercept that was way down there at -42. So looking at the y values, right? I'm gonna have to go all the way down to -42, and I don't want to count down 42 spots. So what I'm gonna do is I'm gonna make a conscious decision here to count my up and down by 5s. So this is -5, -10, 15, 20, 25, 30, 35, 40, 45. That's -45. And that means when I count up, it has to be the same unit, 5, 10, so on and so forth, 15. Now, when I go left and right, I do not have to use the same measurement. I do not have to count by 5s. I can count by 1s if I want. Or if I want, I can do this. I can say that every 2 blocks is 1, then 2, then 3. The important thing is that whatever you do up and down has to be consistent with each other. Whatever you do left and right has to be consistent. So I'm just showing you how there's a little bit of variation in the way our graphs can look. You just sure as heck don't want to be counting down 42, right? That would require a very long piece of paper. All right, I'm going to start with my vertex. To the left, 5, up 8. So 1, 2, 3, 4, 5, up 8. Be careful here. 8 is going to be about here. Again, no man on the moon here. This is just ballpark, right? Good enough. That's my vertex. Let me go ahead and label it. This is -5, 8. And then my x-intercepts are at -3 and -7. So I have an x-intercept here, -3, 0. And at -7, right there, -7, 0. I have a y-intercept down here at -42, which again, I'm going to kind of eyeball this here. 0, -42. And that's it. That's everything I should need to draw it. I'm going to draw my axis of symmetry right down the middle of the vertex. I'm going to try and connect the dots and make this thing look like a U. Come on. Not bad, not bad. Pretty good, actually. And then over here, same sort of thing. Like that. I think that's good enough. Now, look, I understand, you know, it's 2021, right? And I can easily just go to like this and graph it, you know, so you might be sitting there going, why in the world are we going through all this when we have the technology to graph it by hand? And I'm with you, I understand that. I think that the bigger picture here is what is the bigger picture? There's kind of like two bigger pictures to me. One big picture is, can you actually like execute a process, right? If you learn a process of how to do something, can you execute that process efficiently? Because in the real world, you know, an engineer, computer scientist is not going to need to graph a quadratic function. Like, no, but are you going to need to learn a process, set of steps to do something? Absolutely. And so your brain has to be able to work that way. That's one perspective on it. The other perspective is that, you know, if you trust the computer too much, then, and you stop teaching the actual like pure mechanics behind it, and you just trust the computer and the person who programmed it, then you get to a point where you're not quite sure whether or not your answers are right anymore. When I was in school, I had to look into that idea a little more. You know, we talked about how engineers, they use computer programs to answer a lot of questions, to go build bridges and planes. And so one of the projects that I had as a student, I think I was like a senior, was that we had to go pick the three widely used software programs that engineers use or mathematicians use or physicists use. We had to pick 3 different programs. And then we had to look at the way that the program did certain math operations. And then we had to like basically feed the program a problem where we knew that the computer would give us an incorrect answer. So like we could prove what the answer was on paper. Like we say, here's what the answer should be. But then we'd show that the computer gave us the wrong answer. And we would go into the code, the actual like code of the program, and we would exploit weaknesses. Like we would say, oh, look, it rounds here. So it rounds too much. And so if I give it the right input, it's going to give me basically a bad answer. So if you start to get to a point in education where you're not like keeping the foundation here, and you're just trusting computers, I think we get into a dangerous place where we're so far removed from the theory that we can't ever really verify whether anything's right anymore. That's just a different perspective. So, and you have to remember, this is a math class, right? So this is not a math technology class. This is a math class. So if you get frustrated graphing parabolas like I do sometimes, you have to think about, like, you also get frustrated when you're taking, you know, an English class and you have to read some obscure passage that you don't want to read or write a paper. It's just part of studying the history of the subject. All right, we got to move on. I'm just blabbing now. All right, so I've given you pretty nice ones. Everything worked out great. How about something a little more like nasty, right? Let's go with something that things don't just work out great for us. How about this? -5 x squared plus 7x minus 1. I want us to sketch this. It's in standard form, isn't it? So since it's in standard form, I'm just going to identify A, B, and C. And now step one. Step one's always the easiest, right? It opens down. I'm going to start just drawing it so I don't have to write it. We know it opens down. Step two. Oh, like I was saying in the thing we had to do in school where we had to like give the program something and it would give us a wrong answer. We could do that. The other thing we could do is feed it a problem where it would get caught in a loop. And basically we used to say, bring the computer to its knees, basically. So it would just start like it would try and process the answer and it would just get stuck. So like either one of those were valid. You just basically want to break the computer, the program.
Breaking
Right.
a computer program is very easy.
Yes, it is. But when these things have built-in functions, right, where you're putting in specifications for like a beam for a bridge, right? These programs are very, very special, tailor-made, where the only input they're taking is, you know, numbers, right? So you feed it some numbers and then it spits out an answer. If your input's restricted, I'm not talking about like going in and changing the code. I'm saying run the program, give it the 5 inputs at once, and then make it do something bad. Does that make sense? I think you're right. It's still easy to break things, but it's not simple for the things that we were trying to do. Trust me, it was not an easy thing.
I believe it.
Yeah. Okay. So here we go. It opens down. How about the vertex? Well, unfortunately, it's not in the pretty form, right? It's not where we can just see H and K. So we have to use a formula. So the H is equal to -b over 2a. I'll put the formula there again. What's -b for us?
-7.
So -7, good. Over 2 times a is -5. So this is -7 over -10, which is 7 over 10, which is not a nice number, is it? Like it's not a nice like 2 or -5. It's a fraction. We could convert that to a decimal, 0.7 if we wanted to. And see, the thing that sucks now is we have to find K, but K requires that we take that answer and plug it into the original function, right? 0.7. So things are going to start getting messy here because we're going to have decimals. Okay, that's life. Move on, we keep going. So we're going to take 0.7, we're going to square it. We're going to take that, go add 7 times 0.7, then we're going to subtract 1. So yeah, we might need our calculators. And as soon as we start using calculators, you know, there's always going to be some rounding error here. So we have, I'm just going to work this one in detail the first time. I square the 0.7, I get 0.49. Plus this one is also 0.49, then minus 1. No, not 0.49, I apologize, 4.9. And then -5 times 0.49, we get -2.45 plus 4.9 minus 1. I'm getting 1.45. Anyone else get that? Anyone else?
Yeah.
Yeah, so look, I'm going to show you all real quick, because again, this can be frustrating, the technology, because it's here. Watch. I'm just going to have this graph this real quick. Negative, what was it? Negative 5x squared plus 7x minus 1. Was that it? Was that it? I feel like I'm missing something.
You forgot the 7.
7x. Okay, there's the graph right here. You see this? That's the graph. The computer's already done it for me. Not only does this software, this is a website. I can just hover over this and look, it even draws the point for me. Look, I can just hover over it. It tells me the vertex. I don't even have to ask it. I hover over, it tells me the X-intercepts. Look at that. Y-intercept. I mean, these websites have come a long way, trust me. All right. You used to not be able to do this that easily. All right, so here we go. So our vertex is the point 0.7, 1.45. Now I need to see if I have any X-intercepts. So I need to do a quick sketch. Let me do my quick sketch over here. My vertex is 0.7, so to the right, 0.7 and up. So I go right, 0.7, up 1.45. Here's my vertex, and we open down. Again, 2 X-intercepts, right? That it won't always be this way, but I want to start with at least some examples that we do have this. And now we have to find them. So we take the function and set it equal to 0. Why don't you take a minute to see if you can get the correct X-intercepts? You'll need a calculator probably. And you're also going to need the quadratic formula because this does not factor. Let me grab it for you, just in case you don't know it. Okay, so everybody work on this. I'll call on 2 people randomly to make sure everyone's trying at least. See if you can get these 2 with the quadratic formula. How much time do you want? 30 seconds? Yeah, we're getting some people finishing up. Okay, I don't know if that's enough time. But I'm gonna write out at least what your first step should look like. That should be everything plugged into the quadratic formula. And let's see, I know Tavi, you had 2 answers. Anyone else get answers they want to share?
I got 2. Yeah.
Okay, give me one of them.
One is 1.136.
1.136.
Yes.
Okay, and what'd you get for your other one?
0.264.
0.264. Okay, I'm not sure if those are right. They're different than what someone else got. Someone else got negative 0.1306 and 1.5306. So, maybe we need to work through it. We can look at the graph and see which is right. 0.161, 1.24. There might be some rounding issues here. I don't know. I think we're gonna have to go through it. Let's do it. X equals -7 plus or minus the square root. Let's see, did I type it in right? Yeah, that was right. Okay. So I square that, I got 49. Now, this is the part that I think most people have an issue. If they're going to have an issue, it's right here. These all together. 4 times 5 times 1 is 20, but do I add or subtract it? Am I adding or subtracting 20?
Subtracting.
Subtracting. So how do you know it's subtracting? How are you doing that? I'll tell you how I do it, but how do you do it?
Because there's 3 negatives, which
That's the way I do it too. I see 3 negatives. 3 negatives will become a negative, so it'll be subtraction. If you saw 2 negatives, it would be a plus. So minus 20, and then over the denominator, which is -10. So this becomes -7 plus or minus the square root of 49 minus 20 is 19 over -10. Now I need to figure out what the square root of 19 is, and I need my calculator for that. So I take the square root of 19. Make sure you can do this on your calculator. This will be -7 plus or minus. This is where rounding comes in. I'm gonna go 2 decimal places. 4.36. All over -10. And now this is going to be, yeah, go ahead.
Would that not be the square root of 29?
What did I put? Oh, yeah, it is 29. Thank you. That would have been a disaster. Thank you very much. So that changes that. 29 raised to the 0.5. That is 5 points. Still going to round 2 decimal places. 39-ish. So now the plus case, I take -7, I add to it 5.39, and I divide by -10. When I do the minus, it's -7 minus 5.39, and divide that by -10. So the first one there, we get -1.61 divided by -10. And the other one is -12.39 divided by -10. So when you do that, you should get positive 0.161. And this one, you should get 1.239 or 24. Is that what it had? I think it did.
Yes.
Right, yeah. So everyone, this is the part where you don't want to mess this up because this is just arithmetic, but it's the part that everyone messes up. Okay, so just be careful with it. Like you saw what I did, I put 19 instead of 29. So just be careful. All right, Y-intercept is next. So for 5, the Y-intercept, all we do is plug 0 into the function. That should be easy because it's a standard form. So when you plug in 0 here, you just get -1. And so I'm ready to graph. So when I go to do this graph, I think I'm going to make sure that nice space here. What was the vertex? I forgot, it's been a long time. 0.7 and 1.45. So again, we're going to just eyeball this. Let's say this is 1. We'll say this is 2 up here. So 0.7 is about right there. I go up 1.45, it's about there. No, that's, yeah, that's right. This is 1. So 1.45 is about right there. So this is 0.7, 1.45. I have X-intercepts of 0.16 and 1.24. So 0.16, again, I have to eyeball this. 0.16 is about right here. And 1.24, wait, was it 1.24? Yeah, 1.24 is about somewhere around here. I'll label these 1.240. This one is 0.70. No, not 0.7, 0.160. And then a Y-intercept of -1, which is here. Axis of symmetry. And then we draw our problem. Y'all doing all right with this?
Why do we draw the line of symmetry?
It just helps us because what we don't want is something like this. Like, let's say you're doing your work. And let's say you get your vertex to be here. And let's say you get an X-intercept here and here. And let's say your Y-intercept is there. You draw your axis of symmetry. You draw your left side. And then you go to draw your right side. The axis of symmetry is just there to help you see that something is wrong. Can you tell something is wrong here?
Yeah.
Yeah, this point needs to be further out, or this point needs to be further in. Something is messed up. So the
Okay.
axis of symmetry is just kind of like a thing that helps you to say, yeah, that looks good. So like this right here, like, yeah, it looks good. The left and the right balance out, everything's great. I mean, without it, you probably know that too. You don't have to draw it, okay? You'd still know, but it just kind of helps. It's a guide. It's not part of your graph. Okay. All right, I want to do 2 very quick ones. How about this? 4x minus 3 squared plus 1. If we were asked to sketch this, I'm going to go really quick through this. The first step is that it opens up. And I know that because of this 4, right? How about vertex?
3, 1.
3, 1, because this is in vertex form, so I can identify it easily. The opposite of this, and then 1. Quick sketch. My vertex is to the right 3 up 1, right 3 up 1, put a dot, and it opens which way? Up. Uh-oh. I have no X-intercepts, right? I have no X-intercepts. So I skip step 4. right? And I go straight to step 5, which is the Y-intercept. We get that by plugging 0 into the function. And just be careful there. You're going to get -3 and square it. So you get 4 times 9 plus 1. And that's 37. And that's it. From that, you should be able to draw the sketch. There's no more information you need. You have a vertex at 3, 1. And then this is way up at 37 for a Y-intercept. So I'll count by 5s. 5, 10, 15, 20, 25, 30, 35. Here's 40. So 37 will be somewhere around there. And this is where I think the axis of symmetry actually may help a little bit, because you only have 1 point to go off of. So you're going to have to do something like that. And then on the other side, you don't want to be doing, you don't want to do this or this. You want to try and make it look nice and symmetric. So, good enough. So with no X-intercepts, we can still graph it, right? With no X-intercepts, we can still graph it. We just need at least the Y-intercept to be able to draw it. Okay, I think that's going to be sufficient for this. Yeah. Okay. So, off topic, on topic, I have a little question for you. So this whole idea that if you have a quadratic equation, right, that we have a formula for this. This quadratic formula, right? This thing is awesome, right? Helps out a lot. That will solve any quadratic equation. You may recall, if you've studied this in the past, that there are some times where this part in blue, when you start plugging in A, B, and C, that this turns out to be a negative number. And if that happens, you have to take the square root of a negative number, which is not allowed, right? That would correspond to a graph of a function that did not hit the x-axis. So if you had this graph, okay, let's say we were given this function and you went and actually tried to find the x-intercepts, you would do the quadratic formula and you would get a negative under the root. And that's how you would know that it doesn't hit the x-axis, okay? So the reason I'm bringing this up is I have a separate question for you. This is a quadratic equation, right? And we have a formula for it. What if I had a cubic equation, which we haven't studied cubic equations in any depth, but just think about what a cubic equation would look like. It would be a number in front of x cubed plus a number in front of x squared plus a number in front of x plus a number by itself equals 0. Do you think that there is a formula that will give you the solutions just like the quadratic formula? What do y'all think? You think there's a formula for that? Yes, Adam says yes.
Probably.
Yeah, there is. Okay, there is a formula. Now, you're never going to learn it, and here's why. Here's the cubic equation formula. Let's just go to the first website we see. Oh, there it is. So here's the equation for the quadratic formula, right? If you have a quadratic, ax squared plus bx plus c equals 0, here's the quadratic formula. Now, if you have a cubic one, here it is. Wow, right? That's crazy. So it exists, but it is nasty. X is equal to the cube root, not the square root, the cube root of all of this plus the square root of all of that, plus the cube root of all of this minus the square root of all, wow. Oh yeah, minus b over 3a. That is insane, right? It was discovered in 1545, so this is old news, all right? But it is it exists. Okay. Well, what about the fourth? What about a fourth degree? Ax to the fourth plus bx cubed plus cx squared plus dx plus e. What if we had a general fourth degree? Do you think there's an equation for this?
Yes.
Yeah? Let's see if there is. Fourth degree. Fourth degree equation formula. Yeah, that should work. Is there a general formula for solving fourth degree? Yeah, quartic function. Yeah, let's go for it. Where is it? Where is it? Where is it? There it is. Yeah. How about no thank you? Yeah, it's they don't even fit it on this page. They have to have like a separate PDF file for it because it's so massively that. I want to see if there's a better version of it. Let me see if I go to images. I might be able to find it this way. Yeah, that'll do it. That's there we go. There we go. All right. We can do that. We can do that. Looks like a good homework problem, right? Holy crap, man. That's insane. But
I
it
would just
exists.
take the 0.
What's that? Yeah.
I would just take the 0.
Just take the 0. I hear you. I hear you. That's torture. Man, someone figured that out. That is nuts. Okay, so there's a fourth. Do you think there's one for the fifth?
If there is, I don't want to see it.
If there is, you
Unfortunately,
I
I
was gonna
do
say.
believe there is, because they seem to be growing exponentially.
yeah, there isn't. Okay. Now, I'm not saying that there isn't in the sense that we haven't found it. Okay. I'm saying there isn't as in it's been proven that a formula cannot exist. That's totally different. It's one thing to say, hey, I've never seen a pink elephant, right? Because you've never seen a pink elephant. That doesn't mean a pink elephant doesn't exist, right? But we're not saying that there's no formula because we haven't found it. We've actually proven that you cannot have that formula ever. And it's actually for any power past 4. Any power past 4, there is no formula for. Pretty cool. So we should be happy that we have the quadratic, the third degree and the fourth degree, even though they get worse and uglier and uglier, because those are the only ones we have. All right. So here's what we're going to do. It's been a very tough week for me. I'm exhausted, completely mentally, physically exhausted from this week. And some of you have asked about my wife. She's okay. I'll just give you a real quick rundown. She's taking not an experimental medication, but it's medication that is FDA approved, but it is usually not used to treat what she has. And she went to a different type of medication in the last 3 weeks. And one of the side effects is blood clots. You can get blood clots in the brain, things like that. So she woke up with a headache that day. She didn't go into work because her grandfather had just passed away the day before. So we were like already tired and worn out. She woke up with a headache. And then when I was in class teaching, her vision started to like tunnel in to nothing. And so she panicked because she was thinking she had a blood clot. So I ran home and we got her to the emergency room and they ran a bunch of CT scans and, you know, she's fine. It was probably a migraine, okay, which is good. But without knowing, anything that happens to her could be a side effect of the medication. So she has to be like really sure it's not just a headache. So we're hoping it was just a headache. But so she's okay. So just to give you a heads up, but saying that, she has her new treatment tomorrow. So who knows what the next week or 2 or 3 holds for us. But I appreciate you all understanding. And I've never walked out of a class like that before, ever. I've never just had to be like, bye. So that was weird. Yeah, so we are on quarantine still. We're supposed to go back on Monday from what I've heard. I sent you an email with the thing. We're all supposed to fill out this form, and I've been through the form and it's confusing. I understand. Just do your best, okay? What I'm confused about, and I don't know if you all have had the same experience, is that it says that we cannot return to campus for 10 days. Right, something like that. That's what the email said. Did y'all get the email or no? Not the one from me. Did y'all get one from the school?
After
Uh-huh.
I called them, I did, and it does say 10 days or 7 if you get a COVID test.
Yeah.
But it's
So-
like from the day of exposure. So
Yeah, so mine said that I can't come back for 10 days, but I could come back within 5 days if I take another test and I'm negative, right? But if I can't go on campus for 10 days, then am I allowed to go take a test? You know what I'm
You would-
saying? Like, I'm confused about that.
you would
So,
have to go take a test at one of the other like free COVID testing sites. I got an email about it and I can link it in chat. The site that
Okay.
I was given.
so you couldn't go on to campus for a test. You could go to some third-party place and get tested.
Yes.
No, I'm not gonna do that. So,
Fair.
yeah. So my plan is to come back on Monday, okay, which will be past 10 days. And I will go in on Monday and get tested. So I'm just gonna act like everything is back to normal on Monday, but I'll go in and get tested. Unless something changes, that's my plan. Now, if you still feel uncomfortable going on campus, or you are like, you know what, I'm not gonna be able to do what they need me to do, I'll do the Zoom from class, like from campus, to accommodate everyone. But I'm just letting you know my plan, all right? Now, in terms of our schedule, I have not quite completed the quadratic part, okay? So we are continuing to drop behind here, right? We had our test. We are still pretty far behind because we talked about quadratic functions and their graphs. We need to talk about quadratic inequalities, then get to polynomials. So I think what I'd like for you to do tonight for homework is the 4.3, and I'm gonna go try and do that myself because I have not looked at it to see what it's like. But what I did today in class is what you should expect on a test. I give you a function, you run through the 6 steps. That's what I want you to be able to do on a test, all right? Any questions? We'll come back, we'll do quadratic inequalities on Monday, whether or not that be on campus or remote, doesn't matter to me. Any questions?
Do the homeworks, do they still have a due date? Like,
Yeah, I'm going in there right now and I'm gonna adjust them right now because I know that they're all off.
and about the COVID thing, I got a call, right?
You did? Okay.
Yes, and they told me to, if I haven't talked to some Will guy, I don't know what his name was.
Mhm.
Started with the W.
Yeah, I think I know who you're talking about. They said the same thing to me too.
They told me not to come back until I talk to him.
Okay. Then, like I said, on Monday, if you haven't done that and you just feel uncomfortable, just don't come. You know, just come on Wednesday or work it out with him. It's gonna be weird because we can't do anything for 10 days, which would put us, I think, it's Sunday. Am I wrong on that? Because it's 26. So today's day 7, 8, 9, 10. 10 would be Saturday. Campus is closed. We can't do anything. So we really can't do anything till Monday. But our class is on Monday, so I'm not sure how it's going to work. I think we all have to get tested before we can come back.
The way it was described to me is that we will get a call on Saturday confirming that
Okay.
we can come back to campus is what I was
Oh.
told, if you haven't gotten tested and called in about being tested yet.
Yeah, that would be good if they call us. I mean, this is crazy. I mean, I can't imagine what these people are having to deal with, like all these, logistics and stuff. It's just nuts. Okay, so quadratic functions is now due, and I'm gonna have to move a bunch of these. So just pay attention to, see, quadratic inequalities, all of these, I'm gonna have to move these by like 2 weeks. Just, I would say, check your emails, over the weekend, Saturday and Sunday, check your emails. I'll try and update you with anything I have that's, useful, hopefully. Let me see, due dates, I want to add, let's add 14 days, apply to the selected ones. Okay. Is it one of those? All right, that should have moved everything that we haven't done far enough away from us to not worry about it. Any other questions? I'm gonna let you go.
I had a side question.
Yep.
So how is it that people find like these quadratic formulas? Like what's the method to find? Because like those are like extremely big like formulas, if that makes sense.
Are you talking about the quadratic or the one that's the cubic?
Oh, the cubic and the so on.
Yeah, so the quadratic can be found easily by, well, not easily, but all you have to do is complete the square and you can get the quadratic formula, right? I could show that to you. I'm happy to show that to y'all, to show you where the quadratic formula comes from. This is a similar, it's a similar process. It's just a lot more complicated because what you have to do, the kind of trick. Have you ever seen the quadratic formula derived before, Adam?
I don't think so.
Maybe it'd be useful if I showed you that, and then you could actually maybe get an idea of how this would happen.
Mhm.
Is that something you want to see?
Yes.
Yeah. Okay, I'm happy to show it. I stopped classes. I didn't want to continue with the next topic. We didn't have enough time to do what we needed to do. So I'm happy to show it. And anyone else that wants to see this, that's fine. You can go or stay. I'll show you where the quadratic formula comes from. Give me just a second though. I'll be right back. Okay. All right, so what we're gonna do is, you remember when we talked about completing the square? It was at the very end, where was it? Yeah, do you remember this? Completing the square?
Yes. I
Okay,
think.
so we did this thing where we looked at the quadratic and then we pulled out a number to make this a 1. Then we took half of this number and created these like magic numbers. Do you remember that? Like roughly, kind of remember it?
Yeah, kind of.
Okay, so I'm going to do something similar to that. So I think the most important thing for you to do here is just like, I'm going to do something and you just make sure that you're okay with it as far as it's legal to do. Okay, like if I do something and you're like, what is that? Like, Don't necessarily ask the why, but ask the, ask like, I don't understand that algebraically. If there's a problem. So I'm going to first pull an A out from everything. So when I pull out an A, I have to take the B and the C and divide it by A. And that's because if I distribute this A back through, I need to get back this. So I'll get A squared. These A's will cancel. I get BX, and then this A to here, they'll cancel, and I get the C. So is that step okay with you?
Yeah.
Yes. Okay. So we're all good up with that. Everyone's good. The next step is and this is the thing that's weird. I'm going to take this number in front of X, B over A, and I'm going to divide it by 2, because that's what we do when we complete the square. Dividing by 2 is the same as dividing by 2 over 1, which is the same as multiplying by the reciprocal, so 1 over 2. So instead of division by 2, I multiply by 1/2, and this gives me B over 2A, right? That's my first magic number. Now, my second magic number is I take that and I square it, which gives me B squared over 4A squared. That's my second magic number. Okay, so everything I did here is kind of like, again, like, why in the hell are you doing this? Well, this is why. Watch. If I now rewrite this, and right here, after this term, I'm going to add a 0 here. I have some hidden 0 right here, but the 0 I'm going to put here is not 0. It's going to be this. It's going to be that magic number right there. It is, I'm going to add B squared over 4A squared, and I'm going to subtract B squared over 4A squared. Now that's very crazy that I'm doing that, but do you agree I can? Like, this is still 0, right? Now, the next thing I'm going to do is I'm going to realize that the first 3 terms, I mean, these first 3 are a perfect square trinomial. Now, this is not obvious, so I'm going to convince you of it this way. If I take X plus this first number here, B over A, B over 2A, if I asked you to square that, then you would do X plus B over 2A times itself and FOIL this out. So you get X squared, then you get plus B over 2AX, then here plus another B over 2AX, and then the last multiplication would be plus B squared over, so B times B, and then 2A times 2A would be 4A squared. You can put these two together because they both have the same denominator. And so you get X squared plus 2BX over 2A plus B squared over 4A squared. The 2's cancel. And so this thing up here squared, right? This right here squared is equal to this. But do you see that that is this? X
Yes.
squared plus B over AX plus, okay, so by doing this weird voodoo stuff I did over here, I found a way that I can rewrite this thing right here in blue as this right here, as X plus B over 2A, that quantity squared. That takes care of these first 3, right? Now I'm going to see what I still have here. So I still have the, I'll do it in black. I still have the minus B squared over 4A squared, and then plus C over A. Close the parentheses, equals 0. Still with me?
Yes.
Okay, now what I'm going to do is distribute the A through. So the A is going to go plop in front of that parentheses, the A is going to go through to that, and the A is going to go through to that. So when I do that, I get A times X plus B over 2A squared minus B squared over 4A. And that's because when I multiply this by A, one of the A's cancels. And then when I multiply this times this, the A's cancel completely and I get C. So is that okay?
Yes.
All right. Next step, I'm going to move these two guys right here to the other side of the equation. So it'll turn into positive b squared over 4a minus c. Almost there. I'm going to divide both sides by a now. The a's cancel. Getting so close. Okay, when I divide this side by a, it's the same as taking this side and multiplying by the reciprocal. So I'm kind of shortcutting this. Instead of dividing by a over 1, I'm going to take that and multiply by 1 over a, and then distribute. So when I do here to here, I get b squared over 4a squared minus, and then when I do this times c, I get c over a. All right, I'm going to get a common denominator between these two. So I'm going to multiply this by 4a on top and 4a on the bottom. That way they both have a 4a squared on the bottom. Are y'all starting to see it? It's starting to come to life here.
Yeah.
The top is now b squared minus what?
4ac.
4ac, that sound familiar? Over the common denominator 4a squared, right?
Oh, okay. Yeah.
Now I'm going to take the square root on both sides, which will give me plus or minus, won't I? Have that? So x plus b over 2a equals, now when I do this square root, I'm going to do them separately. So I'm going to do the plus or minus on the top over, so square root of the b squared minus 4ac over the square. So I'm doing the square root of the top, here it is, and then the square root of the bottom. But what's the square root of the bottom?
2a.
2a, right? One more step, move this to the other side. Well, two more steps. When I move that to the other side, it becomes minus b over 2a. And then I still have all this, which I can write as plus or minus square root of b squared minus 4ac all over 2a. But they both have the same denominator. So you put them together. Negative b plus or minus the square root b squared minus 4ac all over 2a. There it is.
Wow.
Yeah. So it's definitely within the ability of humans to do that, right? I mean, now, how would you ever come up with this, right? How do you ever come up with this idea of completing the square to make it happen? How does that happen? Well, somebody suffered for a long time and figured it out, okay? With the cubic equation, it's a similar sort of thing. You have to be able to do things, see a hidden zero in here that allows you to do something similar to this in order to get your term isolated out like this. It's just nowhere even close to easy. I'll be honest with you. I've done it once in my life. I've proven the quadratic formula many times. I can do it without even, I don't have to look at a reference. I can just do it out of my mind. The cubic, I've done it once in my life. It was in a class called complex analysis. And since then, I honestly have not done it. So I could not show it to you right now because I would have to go back and look. But I know that it involves a way more complicated approach than this. And this is already pretty complicated.
Mm-hmm. Yeah,
I'll look into it. If you're interested, I'll look into it. If it's within the grasp of what I think people can understand, I'll do it. But you'll have to give me some time to reference some of my older material.
Okay.
Does that sound like a good place we can leave it?
Yes, I didn't think like you, what's it called? I didn't think like, what's the word? I can't. It's really like interesting to see how it goes full circle.
Mm-hmm.
And that like, I never thought like you could be able to like incorporate so much in one equation, if that makes sense.
Yeah. Yeah.
Really interesting.
What's really, I think, even more interesting or just equally interesting is the fact that for a 5th degree, we don't have a formula, that it doesn't exist. Proving it doesn't exist, that's a very, very interesting thing, you know, because like I said, it's one thing to say, hey, we just haven't found it, you know, hopefully one day someone finds it. But to prove it's impossible to find it is kind of cool. How do you prove that? Like, how do you prove it's impossible to have a formula? That's a much more difficult sort of concept to wrap your head around.
Yeah.
Yeah. So it's kind of like this. It's kind of like, and I don't have a good analogy for this because it's the way our logic system works. Like I was talking about the pink elephant, right? It's one, like, how do I prove that there is not a pink elephant? That there's no such thing as pink elephants, right? How do you prove that? Well, how do you prove that? How do you prove that there are no pink elephants?
You could
You would
try an indirect proof. Not sure how it would work.
I mean,
Try it.
just because you've never seen one or no one's ever seen one doesn't mean they don't exist, right? So how do you prove that it's impossible? What you would have to do is you would have to say, okay, assume that a pink elephant exists, right? And then somehow contradict yourself. That's the way mathematical logic works. Is the way that you prove that there is no formula for x to the fifth is that you assume it does, and then you wind up contradicting yourself. And that's called a proof by contradiction. And that's the way that it is shown, but it's very complicated to do it. So anyway, we're getting off topic into logic and things like that. But if you're interested in those sorts of things, you know, math is definitely something, once you start getting past the mechanical parts of math gets very theoretical, and there's a lot of thinking that goes involved with it. A lot of logic, a lot of proofs. So are you a computer science major, Adam? What's your major?
Actually, yeah, I'm gonna go into computer science.
Yeah, so what happens is, like, you know, when you're in undergraduate school, computer science, they study their thing, math majors study their thing, right? But once you get to the graduate level, computer science graduate students and math science students are basically doing the same sorts of things. Like we are both doing logic, because when you write programs, it's all logic, right? It's all logic. And so mathematicians are doing the same sort of thing. We're doing all logic. We're trying to do proofs. We're trying to understand when a statement is true, when you can prove something, how you can or can't prove it. So anyway, computer science is a good place for you if you like that sort of thinking.
Yeah, it's just two different methods going to the same road, basically.
Yeah.
Is it?
All right, everyone, I've got to run, but nice chat, and I'm glad we were able to do this. I thought about doing this in class, but I was like, nah, we won't do it. But I'm glad you asked, because I'm always open to doing this, because this is pretty cool. I mean, quadratic formula is something that you've seen so many times. You use it all the time. It didn't just like show up in, you know, some scroll that was given to us by aliens, right? Like we came up with it, you know, there it is. Took us what, 15 minutes at the most? So, all righty, y'all have a good one.
You have
Bye, thank you.
Bye.